Hello everyone, my name is A.H.Qureshi and I'm going to present our algorithm called NeRP, a neural rearrangement planning method for unknown objects. We address the challenging problem of finding an executable task plan given only the RGBD information of the current and desired scene arrangements. Moreover, we assume that the number or types of objects, including their geometry, poses, and correspondences between current and target scene objects are unknown. To address this difficult problem, we propose NeRP, a learning-based planner for rearranging sets of unknown objects given only a current RGBD image and RGBD image of a goal configuration. We show that our method works with never seen before objects and generalizes to solving the real-world rearrangement tasks such as shown in this video, where NeRP is generating actions to rearrange three objects to get to the desired arrangement. The most relevant work to our method is perhaps the field of task and motion planning that generally relies on model-based methods using non-objects and fully to partially observable domains, which limit their applications to practical problems arising in the real world. Recent advancements, however, have relieved this assumption to an extent but still depend on either multiple demonstrations of the same task or fail to generalize to long-horizon multi-step predictive problems. Now we present our proposed solution called NeRP. NeRP comprises several modules. The scene generator outputs the scene graph given the current and target RGB information. We use unknown objects instance segmentation, also known as UCN, to extract a specific RGB information and their corresponding point cloud for each object from the given scene. The RGB information for each individual object is passed through a pre-trained resonant model to compute their features that are then used for object pairing in the current and target scenes. Finally, the point cloud centroid of the paired object in the current and target scenes are calculated, forming a node in the undirected scene graph. The generated undirected scene graph is then given to a higher order graph neural network known as KGNN to generate node embeddings. The object selection network takes all the node embeddings and select a node for the next step prediction. This node corresponds to a particular object in the given scene information. The delta proposal network is a stochastic model that uses dropout during execution to generate a variety of potential translations for the selected object, from which NeRP selects the best option. The goal satisfaction network takes these delta proposals and the selected graph node embedding and predicts scores indicating whether the goal has reached for the selected object. The clear network is a PointNet++ based module that takes two point cloud sets and predict if they overlap or not. We generate these pairs between the selected object's future placement and other individual objects' current placement point clouds. Finally, given delta proposal, goal satisfaction, and Clean scores, our predictive planning algorithm generates a Clean free placement mask for the underlying controller to execute the placement action, which leads to the next scenario in an iterative rearrangement planning process. We train NeRP using synthetic data with randomly generated scenes containing only 5 objects as shown in these example initial and target scenarios. Once trained, we evaluate NeRP on unseen synthetic environments with 3 to 8 objects and demonstrate its sim-to-real generalization in multiple challenging scenarios. Now we show few examples of NeRP solving various never seen before rearrangement tasks in both simulation and real-world scenarios. Example Sim 1 shows NeRP generating task plans in a simulated environment for the rearrangement of 5 objects to get to the target arrangement. It predicts their multiple candidate placements that appears as a blob and selects the best Boolean-free placement with maximum goal satisfaction scores. Example Real 1 shows NeRP solving a 2-object swapping task through sim-to-real transfer. And example Real 2 shows NeRP rearranging 5 objects, which is again through sim-to-real transfer. In conclusion, NeRP can rearrange unknown objects to reach the desired given arrangement using only the RGBD data. However, it relies on scene segmentation and correspondence matching techniques, which we observed often fail in real-world experiments, as shown in this video. Therefore, in our future work, we plan to augment NeRP with robust segmentation and correspondence matching techniques, and also extend it to do set-based planning in SE3 spaces.